Hey, John,
Yes,
are we going to have class tomorrow afternoon?
I don't know
Okay.
because they are going to have a meeting tonight at about 9 o'clock. So make
Ew.
sure yeah, I know. Make sure you're checking your Ivy alerts and your email.
Gotcha.
So I have a feeling that I don't know if it'll come fast enough, but if it does and is as bad as they say, then we'll probably be starting the day and then leaving early. But
Gotcha.
that's my best guess right now. Okay.
Okey-dokey.
Okay. Okay, I'm assuming everyone can hear me and see my screen.
Yes.
Okay, thank you. Let's give everybody a couple more minutes. It's 5 o'clock. I don't expect tonight's lesson to be very long. It's going to be maybe 30-40 minutes tops. And then you've got some work to do to go along with that. So I'll finish attendance here and we'll get started shortly. All right, it's 5:03. I'm going to go ahead and get started. There's someone else just showed up. One more. There's David. There we go. Gotcha, David. So that means that's at 14. So, okay. So, just so we don't keep all of us here longer than we have to be, we'll go ahead and get started. And I'm sure several of you are wondering about the weather tomorrow and what that means for school. All I can tell you is that I've been sent messages to prepare virtual lessons. So that just means I'll be sending an email out with some stuff, and we may have a little short meeting if that's the case. It depends on what really happens tomorrow. Everything looks wonderful outside right now, but supposedly it's going to ice really bad tonight, and they're going to make a decision tonight at 9 o'clock if they're going to have campus open or closed based on the forecast. I don't know. My best guess is that the day will probably go on like normal. They don't usually cancel things unless it's obviously really bad. We wake up in the morning and it is really, really bad. But it might not get bad until later in the day tomorrow. So we may start stuff on campus tomorrow, and then the campus will be closed and we'll all have to go home. So that's happened before too. So I'm not sure what's going to happen any more than you guys are. Just make sure you're checking your announcements, checking your IV alerts and your email to make sure that you know what's going on, so you don't end up driving to campus and there's nobody else there. So, okay. All right. So as far as I know, when you guys click on this, you should only still see just 2 modules here. So all we are is on week 2. And so all we need to do is click on module 2. Let's take a look at our syllabus. We click on that. Watch your eyes. You see week 2 is a really simple lesson. For those of you that have had plenty of electricity classes, this is going to be nothing for you. For those of you that are new, and we've got still several of you that don't know a lot about electricity, this is just a refresher course. It's not all that we're doing, but the lesson is just called What is Electricity? So it's just going to be making sure everybody understands current, watts, volts, things along those lines. And it's pretty basic is what I'm trying to say. Then you do have some challenges. You do have an electrical grid symbol quiz. We'll talk about that. So that takes it up a level a little bit. And then for our virtual part of our course, you have a video on Thomas Edison. So it's not got quite as many quiz questions as the other one. I think it only has 19. So you should have to watch about the first hour of that. It's a little longer than an hour if you want to finish the documentary. That's great, but we're learning about where the grid came from, who are the people that were the ones that were pioneering the grid, and how we got to where we are today. And it helps to watch those documentaries because you get a better idea overall of how we got the grid built, and what's coming next is going to be the next question we're going to ask. Okay, let's go back. So if we click on module 2, that'll take us to our overview. We have a PowerPoint tonight called What is Electricity? And then we have our documentary that we watch on YouTube. And then you have your electrical grid symbol worksheet for the quiz, with a quiz. So your assignments is a short lesson on what is electricity. You'll watch your Edison quiz, you watch your Edison documentary and take a short quiz over that. And then you have a grid symbols quiz. Now this grid symbols quiz has pretty much unlimited attempts. So it's not to make you feel like you don't know what it is that you're doing. It's to give you a chance to look at a print from a real switch yard and see what the symbols are on the print. And you have a legend to go along with it. So it's just a matching, and you can get it, do more than once until you can get it right. So it shouldn't be too much. That's a little bit more of a challenge than probably your homework. So let's just dive in. Is there any questions for me or concerns before we get started? Looks good. So the first question that we're going to ask is, what is electricity? What an electrical current is, how electricity is used to perform useful tasks, the physical delivery system of electricity, the key physical properties of electricity, and the 4 key physical sectors of the electric business. So those are the things that you want to try to learn tonight in the lesson. So the first question I have is, can anybody explain to me how electricity works? Does anybody have any good ideas? What makes electrons flow? Usually don't ask too many questions, but I'm going to try to challenge you guys a little bit.
It's the current, isn't it?
Current is the flow of the electrons. Yes. So I'm going to walk you through this a little bit to kind of help spur some thinking. As we look at this picture here, we can kind of see atoms. That's what we're looking at. We're looking at, let's say that is a copper wire, and those atoms are copper atoms. And the electrons look like they're moving from one atom to another, and that's exactly what they are doing. But what is going to make them move? Do any of us understand that? What is making that electron move from one atom to the other?
I would imagine some kind of like
voltage.
Voltage. I heard one answer, voltage. What was the other one?
I was gonna say like an electromagnetic force of some sort.
Ah, yes, electromagnetic force or voltage. So voltage is the correct answer. Electromotive force is also the correct answer. So what happens in a solar panel? Do you guys know? What is moving the electron in a solar panel? Sunlight, right? But what is it in sunlight? Do we remember? Do any of you guys know? What is it in sunlight that actually makes the electron move?
The photons?
That's right, photon. See, I got a chat question here. Heat. It's partially heat. Yes, I mean, these electrons get excited, and that creates heat. Sunlight is heat. Sunlight's coming from the sun, which is a big ball of fire, right? And that's what spins the electrons, or I'm sorry, it spins the photons out. An electromotive or electromagnetic force, if it's not a solar panel, then how is it moving? What about in a generator? Yeah, electromotive force. Yep, that's correct. So if you have a generator, that was in the chat. If you have a generator, then we've got magnetism, right? Magnetism is going to push off these electrons, but what makes it a conductor is the fact that these copper electrons, these electrons right here, are loosely held, and there is an extra spot for an electron in this outer shell on the atom. So we're just trying to clarify that magnetism makes these things hop if we're talking about a generator. So a magnet, we rotate a generator around in a circle, and it makes these move with every rotation. They'll either go this direction, or they'll go this direction if it's an AC generator. So it goes back and forth, depending. And then if it's a photon, it's going to be a DC current. So it's going to flow in just one direction, like the picture's showing. But good answers to some of these questions. Let's pick away at these slides a little bit. So electrons are tiny negatively charged particles found in all atoms. So they're negative. Positive is going to be your protons in the center. If we have more negatively charged particles, if we have more electrons than we have protons, then we have what's called an ion or a negative ion. If there's more protons than there are electrons, then we have a positive ion. So that's where we start to change the form of an atom. So if we're talking about working with a battery, we're simply taking an electrolyte and we're separating it into positively charged ions versus negatively charged ions. And we separate them, and then when we hook the battery up to a load, like a light bulb, we create a path for those electrons to flow. The opposite charges are going to attract, opposites attract, right? So the negative's going to flow to the positive, just like you're seeing in this picture. So electricity is transmitted as loose electrons move from one atom to the next within a conductor. A conductor is any material that facilitates this transmittal of electricity. The rate at which electrons flow through a conductor is called current. So make sure you understand that. Keyword is rate and electron flow. That is current, and it's measured in amps. The force that moves electrons through the wire, as we've identified, is called voltage. It's the pressure. If we're thinking about electricity, like if it were a hose of water, the water, or how fast the water is coming out of the hose, is the current rate. But what's making the water move is going to be the water pressure, or the voltage, the force that pushes those electrons through the conductor, or the water through the hose. And then resistance is going to be the size of the hose. If the hose is a really large hose, it's going to take more force, more water pressure to move more current through that large hose. Just like if it were a wire, if we had a large wire, it would take more voltage to move more current through that wire. So we have a simple circuit here where we go from negative to positive right through a bulb. What happens is we're trying to push too much current through a hose that is too slow. So my internet just said it was unstable. Let me do a quick check here. Oh, looks good on my end. All right, I'll keep going. Hopefully you guys can hear me just fine. Ohms are the equivalent to any friction or blockage that might slow the current flow. So that's what we're talking about when we talk about resistance. We're talking about ohms. How many ohms is how much resistance is in a wire or a conductor. Current is always directly proportional to voltage, and resistance is shown in Ohm's law. So current in amps equals voltage divided by resistance. So what that means is current would be maintained in a circuit if you increase both the volts and the ohms by the same ratio. You would increase the current if you increase the voltage, but not the ohms. Conversely, you would decrease the current if the voltage was unchanged, but the ohms were increased. So that's what we mean when we say directly proportional or inversely proportional. One goes up, the other goes down. So there are 6 major types of energy. We need to classify those. There's chemical energy, which is going to be batteries or stored energy. There's electrical energy, which is energy associated with current flow. There's electromagnetic energy, which is what comes from space: visible light, infrared light, ultralight, X-rays, microwaves, radio waves, gamma rays. We also can make those types of electromagnetic waves, like radio waves, the ones that are safe. There's mechanical energy, energy that can be used to raise a weight, move a force. Nuclear energy, energy stores as a result of particles interacting within the atomic nucleus. So we split the atom. And thermal energy, energy associated with molecular vibrations or heat. So those are the 6 ones that you need to make sure you know, if you don't know those already. Any questions so far? Different voltages are used in a circuit depending on what is being done with the electricity. So what we're testing on is just the very basics. So we got a transformer. We want to make sure we understand high voltages are used to transmit electricity long distances, while lower voltages are used to power home appliances and office equipment. So we have a transformer in the middle. What we notice is, what do you guys notice? What is the difference between the high voltage and the low voltage? Does anybody see it? For those of you guys that are experienced, I'm trying to ask some questions.
There's more windings.
Very good, man. Yes, there's more windings on the high voltage. So that means there's more copper atoms. There's more copper atoms. That means well, let's just back off from more copper atoms, but the voltage is going to be stepped down here because it's a change of ratio. So this could be like a 2-to-1 ratio. So if this is 240 volts, that means this would have half as many windings if this was 120 volts going down. But what we got to remember is the current is inversely or directly proportional, right? So if the voltage is going down, then the current is going up. And vice versa, if the voltage is going up, the current is going down, we end up with the same amount of power. Step up transformer, primary and secondary coils. Yep, very good, David. Okay, voltages can be changed through the use of transformers. Transformers are able to change the voltages because of applying electricity to 2 different size coils of wire in near proximity. So you guys watched some of those old documentaries already. Does anybody know who is responsible for inventing the transformer? You should know that now. Well, maybe I'm asking too broad of a question, but the idea, yes. Yeah, but there was one person, Westinghouse, yeah, he is part of it, yeah. But you got to remember who Nikolai Tesla is. So we'll learn about him. See, what we got is, we've got Edison being very famous, and we know we're going to learn about Edison now in tonight's lesson and all the things that he did. And he did invent quite a few amazing things, but the modern grid would not exist in the way that Edison would have done it. It's the way that Nikolai Tesla done it. So next week we'll be learning about Nikolai Tesla. That'll be the last time we do history. But tonight is Edison, and then tomorrow next week, will be Tesla. So is anybody ever confused about when you look at the voltages on a house and they say it's 110 and not 120, or it says 220 and not 240. Has that confused any of you guys? I'm
Is that different,
assuming.
like line loss or something.
Yeah, so it depends. So a lot of it is old school. It's actually, those were the voltages that the power companies were generating. But now they pretty much generate at 120, 240. So if you were to put your meter on there, you would see 120, 240. And it also goes into resistances. So if there is a difference in line loss, 120, 110 would be what it's running on. So try not to be too confused with that. Yeah. Yep. David, good deal. I can see you were watching the videos. Yes. Okay. And then our commercial industrial buildings are going to operate on 480. You might see those buildings or those places working on like 460 volts instead of 480. It's still basically 480. But if the motor only wants to run on a certain voltage, then you may need to have a transformer that steps that voltage down just a little bit. Anyway, 480 volts, the size of a typical electrical service in a person's home is going to be 200 amps. So to begin the flow of electrons through a conductor, a source of energy is required. This can be either chemical or electromagnetic, as we've already talked about, chemical being batteries. There's batteries and fuel cells that operate by using chemical energy to free electrons from one material and transfer them to another through a conductor. Now, I read an article that I thought was really interesting. It was a large freighter in Australia. Did anybody read about a large freighter that is running on hydrogen fuel cells now? We're talking about a big boat. Anybody see that? Okay, well, if you didn't see that, it sounds amazing, but a lot of people are excited about fuel cells. But let me tell you some of the problems with fuel cells. Problem with fuel cell is the hydrogen has to be kept at a very cold temperature. So there's one problem right there. Then we got a ship full of hydrogen. That sounds kind of dangerous. And then you've got to be able to find places to refill your hydrogen. And when they're making the hydrogen, where do you guys think the hydrogen comes from? Does anybody have any idea where they got all that hydrogen?
Probably just water.
Well, water is part of the fuel cell process, yes. But that's the trick. Everybody thinks, okay, fuel cells work with electricity and then you just use water, but you've gotta split that water up to get the hydrogen out of it. And you gotta use a fuel source. So anybody else know? Let's see, check the chat. That would be nuclear. That would be nuclear, David.
Oh yes, I guess it would just be whatever the grid is running, right? Because whatever they need to use to run electrolysis.
Yeah, pretty much. Coal power, baby. Can you believe it? So they're running a boat with hydrogen fuel, but in order to create all that hydrogen fuel, they have to use coal. Or natural gas, or whatever the grid is. Now, if they were using renewable fuels, now we're talking about, okay, this makes more sense now. But I just thought I'd bring that up since they brought up fuel cells. Make sure you look at that when you're looking at the different processes like you're talking about and thinking about. You know, there's just not enough economics there yet for this hydrogen to work. And that's why we haven't seen it really everywhere. We started to see electric cars because they kind of figured out electric batteries. We wanted to see more hydrogen cars, but they haven't quite got it all figured out, how to create the infrastructure, and some places have, got it figured out, but it's just one of those things where fuel cells still have a ways to go. So batteries and fuel cells contain 3 components: 2 electrodes and electrolyte. The electrolyte reacts with the electrode to create oxide that results in a negative charge, and 1 electrode and a positive charge on the other. So again, we're creating a potential difference of voltage between the positive and the negative ions when we charge them. We're separating them out, just like if we were to separate red marbles from blue marbles and putting them on one side or the other. The electrical charge forces them apart, and then when we create a load or hook the battery up, then they start to go back in the other direction. So the imbalance in the charge creates an electric current when the terminals are connected to form a circuit. All right, so here you have some basic vocabulary words. This should be in your homework, real easy. This is where you find your answers. So current, the rate, flow of electrons; amps, the unit used to measure current; voltage, the force that moves electrons; volts is the unit used to measure voltage. Then we've got kilovolts or 1,000 volts. We got resistance, which measures the strength of impedance or what is slowing down the electron flow. Then we have ohms, which is how we measure resistance. And then we have a transformer, a device used to change voltages in a circuit. All right, let me move on. So we got electromagnetic energy is used in 2 primary ways: is to create electricity. So we've already talked about this. Solar or photovoltaic cells are used to make materials that can move electrons. We know the most common way of creating electricity is the electric generator. And we use that in wind turbines. We use that in coal plants, power plants, nuclear plants. The only time we don't use that is if we're using solar. One additional way that electricity is used is to create a value or a principle of control. So that's where we get into microelectronics and modern day electricity. The principle behind transistors and microchips. The amount of electricity necessary to perform useful tasks is determined by the power required to move electrons through a specific device. So what is the resistance of the device? So if your television has a certain resistance, then it's going to require a certain amount of current and voltage to move through that resistance. And that's what we call watts. So this power is measured in units called watts. Power used over time is commonly called energy. For example, a 100-watt bulb used for 1 hour will consume 100 watt hours. The current, voltage, and power available in a circuit are related. So 1 watt equals 1 volt times 1 amp. Very simple formulas. So if your house was only running on 120 volts and you had 200 amps, which our homes actually run on 240 volts. So if it was 120 times 200 amps, then you would have 24,000 watts available to you at your panel, or double that to 48,000 if you're running at 240 volts. So 48,000 watts at one time before your breaker trips. So we have just a couple kinds of electricity we just need to make a note of. We have direct current, which is going to be electricity that moves in one direction only. And that is the type of electricity that Edison pioneered. And then we have alternating current, which alternates back and forth. And it's just moving as the generator turns. So generator on one side is going to be positive. Generator on the other side is going to be negative. So that's how it's going: negative, positive, negative, positive, negative, positive. It's still flowing though, and it works. And that was pioneered by Nikola Tesla. Okay, here. Very simple stuff here, guys. Easy lesson for a night of rain and snow. And flow of electrons or current is created by a generator. The electrons are transmitted to and back through the consumer through conductors. So we have transmission lines being the large lines and distribution lines being the smaller ones that go out to each customer. Transformers facilitate electric transmission because it is much more efficient to move electricity long distances at high voltages. So current at high voltages is very dangerous. It's capable of sparking or jumping large distances. Current is what kills us, is what it's trying to say, causes death. Electrons always make their way back to the source or the generator. That's how we have a complete circuit. Thus, the electrons are never really used up. The reason the electrical systems require continual input of energy is to keep the electrons moving. So we know that electrons cannot be easily stored. So we don't really have battery storage on the grid yet, even though we're getting energy storage and it's coming quite quickly. The electrical system must be operated to ensure that supply and demand are in balance throughout the system. And that's the job of a system operator or dispatch. Balancing authority. If electrical supply is not available to match the instantaneous demand, then what happens? The whole system will crash, resulting in blackouts. Next, an electrical system requires continual surveillance and adjustment to ensure supply matches demand. So that's going back to balancing authorities and system operations. We also need to understand that electrons flow on the path of least resistance, always. If the least resistant path is from the transmission line through a wet tree branch to the ground, then that is where the electricity will flow. If the path of least resistance is from one utility's transmission system to another interconnected utility's transmission system, that is where the electrons will flow. All utilities on an interconnected system must cooperate in operating their systems, as the action of one may cause the electrons to flow into or out of the other system. And lastly, with the advent of modern electrical controls and microchip-based devices, our consumption is no longer tolerates momentary outages or fluctuations. We need electricity to be reliable and constant. The entity that is responsible for matching supply and demand must not only have to do so every minute of the day, but do it with very little margin of error. And that brings us to the end of these PowerPoints. Okay, is there any questions on that? Pretty straightforward, simple lesson. Give us the basics. So there you got 24 questions, or you got your homework here. We'll take a preview of that. It's just going to be true and false most of the time. There are some questions in here. E stands for electromotive force. It does. That is true. Voltmeters are always connected in parallel. If we're measuring volts, that's what we would do. Okay, when we're talking about a series circuit, we're talking about circuits where we're just in a simple circuit. I think you can handle this. You got to remember, voltage is the potential difference of electromotive force and the pressure. Okay, you do have a conversion here where you got to remember to move your decimal point 3 places to the left for a milli. Anytime you're moving your decimal point, you got to move it 3 places. If you're already in one spot, 550 milliamps. Okay, that's your homework. So that'll require you to think just a little bit more. Let's look at the, let me get back out of this. Let's look at the reference for the grid symbol worksheet. So I don't expect you to memorize this at all. I expect you to reference it. We've seen a lot of symbols out there, and we're talking about the electrical grid symbols. So this is new for you guys. We're not going to get into it too deep. We're just going to get started on it and let you kind of see what that would be like if you were to try to read a print. And really, it's just what we're trying to do is get you to identify what the symbols look like on a print for, say, a switch yard or something that a lineman would read instead of maybe an electrician. So there's several of these that are either normally open or normally closed switches. So we can notice normally open means it's white, normally closed shows that it's black. And they may or may not have something attached to them that you don't know what it is. That's okay. This is an open wire. This is what neutrals look like, or single phase wires look like on a drawing, little dash marks. We know that when they cross, they're not connected unless they have a dot right there. And honestly, most of that stuff isn't really what we're looking at. You're identifying things such as a fuse or different types of fuses. Different types of interlocks or types of circuit breakers, lightning arresters. Motors always have an M in the circle. Yeah, a regulator. This is a voltage regulator right here. That's one of the symbols you'll see. Okay. And then you've got windings on here. So these are new. They don't look like a lot of the symbols that you've seen before. So if you want to get into working in line work, if you want to get into grid work, you want to work for a utility, then you might want to take a little extra time and try to learn some of these, because these are the types of things that might show up on a test if you go into an interview. You probably are never going to remember all this stuff, but that's it. There's 7 pages there, but there's only so many symbols. So what is that and what does that go with? Well, let's look at the quiz. So when you do this quiz, it has this picture right here where you just got to label 10 things on here. Now you can hardly see it. The way that you can see this is you double click on the picture and you open it up in a new tab. And then you should be able to see the screenshot. And so you're just going to go through and try your best to identify what these are. That's going to take a little bit of time. But that's going to challenge you and let you learn about these different symbols. Like I said, you got multiple attempts on this, so you can guess your way through it if you want to and try to see if you can figure it out that way. Or you can try to study the legend and try to get it right the first time, which is what I would try to do, and write down your answers as you go along. Any questions on how to do that? hopefully I don't have any problems with that. Let me know if you guys have any major problems with that. See, and it's 5:43. And then lastly is this Thomas and Edison documentary. So all you have to do is really click on this and hit play. And only about the first hour of it, like I said, covers the quiz. So there's a quiz that goes with that, but I'm going, since you have all that stuff that you want to work on, you don't need to hear me lecture any longer than I have to, because normally if we were on campus, what we would be doing is sitting in classroom watching these videos. So you're just doing them at home now. Okay. Is there any questions for me before I let you guys go?
You said we would be receiving an email around like 9 o'clock if we do have class tomorrow and like in person.
Yeah, and I expect it to be chaos. So if you don't know what's going on, just assume that you're coming to campus, but check your email. You check for Ivy Alert. Don't just look for information from me. I might be asleep just like you. They're supposed to text everyone in the morning, or you should get an email to your Ivy Tech email. So everything Ivy Tech, you should get a text if you're on Ivy Alert, and I will make an announcement as soon as I know if we're closing campus. But like I said, I think we're going to end up going, and then they're going to end up shutting us down. But that all depends on if it's not cold outside yet. So it's just going to rain. It's just going to rain, and it's not going to turn to ice unless this temperature really starts to drop. And I know it's going to, but it may not do it by tomorrow morning. That's kind of the catch. So it's going to depend on what the weather forecast is saying. And if it looks like at 9 in the morning, it's still going to be raining and no ice, yeah, they're not going to close the campus. If that helps you and you're thinking about what you got to do for tomorrow. Okay. Any other questions? Well, enjoy the documentary. Thomas Edison is fascinating. It's a pretty good documentary, so I hope it's a good watch. And I will talk to you guys hopefully tomorrow, as long as we don't have a blizzard come too harsh on us. And if not, watch your email, do your Ivy alerts. I'll be checking in, and I will hopefully see you guys then. Have a good evening.
See you, John.
See you,
Or-
John.
You do.
All right. Bye-bye. Bye-bye.